Running a 100 billion parameter language model locally requires moving hundreds of gigabytes of data through a processor every second. This table compares bitnet.cpp against a baseline, Qwen 2.5 1.5b. Bitnet requires just zero point 0.4 gigabytes of memory, achieving 29 milliseconds of latency on a standard CPU. Look at the energy requirement. At 0.028 joules per inference, it operates with roughly 12 times greater efficiency. This efficiency does not require a performance trade-off. Because the 1-bit architecture is so lightweight, researchers can scale the parameter count significantly higher within the same memory footprint. This allows the 2.4 billion parameter bitnet to outscore higher precision models like Qwen 2.5 1.5b on math benchmarks like GSM-8K. These metrics are achieved because the model is designed for this constraint from the start. Shrinking a standard model after it has been trained in high precision inevitably degrades its reasoning. The efficiency comes from the architecture. Bitnet natively trains on ternary weights, constrained to 3 specific values, and runs through bitnet.cpp, removing floating point math from execution. To understand how it runs so fast on standard hardware, we need to look at the execution pipeline and see exactly how those floating point operations were eliminated. By solving the inference bottleneck at the kernel level, Microsoft has decoupled advanced language reasoning from the necessity of expensive, power-hungry GPUs. When a standard CPU runs a language model, the primary bottleneck is memory bandwidth. The processor spends most of its time waiting to pull those heavy 16-bit floating point weights from the system RAM. This schematic shows a standard execution pipeline. High-precision decimal numbers flow from memory directly into the CPU's arithmetic logic unit, specifically the multiply-accumulate gate, to perform the required matrix math. The common workaround is post-training quantization. Tools like llama.cpp compress those FP16 weights down to 4-bit integers after the model is trained. In memory, this works. The file size shrinks drastically, allowing large models to fit inside limited RAM. But that compressed file size masks a severe computational penalty at runtime. Hardware logic gates cannot perform matrix multiplication natively on 4-bit compressed integers. Right before execution, those blocks must be mathematically dequantized back into full floating point decimals. This translation step forces the CPU to burn clock cycles reconstructing numbers, keeping the processor compute-bound and limiting real-world speed and energy savings. Shrinking the file size resolves the storage problem. To achieve hardware acceleration, the arithmetic itself must be simplified. Microsoft's solution is the bit linear architecture, which natively trains models in 1.58 bits from the very first token. Instead of complex decimals, every weight in a bit linear layer is strictly constrained to one of 3 states: -1, 0, or +1. You cannot simply take an existing full precision model and round its parameters to these 3 digits. Doing so destroys its ability to process language, because the model didn't learn to represent information in that restricted space. The network must be built with these constraints active during pre-training, using abs mean quantization. The math is direct. The system scales the weights by their mean absolute value, then snaps them to the nearest integer bucket. At the same time, the incoming activations, the actual data flowing through the network, are quantized to 8-bit integers on a per-token basis. Over trillions of training tokens, the neural network learns how to route complex logic using nothing but these simple ternary pathways. By forcing the model to adapt to a ternary state during training, the architecture eliminates the need for floating point multipliers before inference even begins. To translate this architectural efficiency into hardware speedups, Microsoft released bitnet.cpp, a specialized C++ inference engine. Because the weights are exclusively -1, 0, or +1, traditional multiplication is completely bypassed. An incoming activation simply passes through unchanged, flips its sign, or zeroes out entirely. The developers went further, eliminating the decode activation pipeline by pre-computing results using lookup tables. If you analyze a sequence of 5 activations hitting a ternary system, there are exactly 243 possible outcomes. Instead of calculating the math live, bitnet.cpp loads all 243 answers directly into the processor's AVX512 SIMD registers. As the CPU reads the activation sequence, it can ignore its arithmetic logic unit and pull the pre-computed answer from the memory register. Bypassing the arithmetic step also yields a reduction in CPU cache misses, keeping data flowing smoothly without stalling the processor. This is how bitnet.cpp achieves up to a 6-time speedup. It transforms language model generation from a heavy arithmetic problem into a memory retrieval task. The innovation of bitnet relies on 2 pillars: the natively trained ternary constraint of the architecture and the lookup table execution of the inference engine. This timeline tracks the development from the theoretical paper in 2023 through the bitnet.cpp release in late 2024 to the official 2 billion parameter model in early 2025. The immediate roadmap includes dedicated GPU inference kernels and support for neural processing units, or NPUs. The NPUs embedded in modern smartphones and laptops are designed for matrix logic blocks, making them an efficient environment for these ternary operations. The trajectory of bitnet suggests the future development of specialized 1-bit AI accelerators. Silicon designed exclusively to handle simple additions and memory lookups requires fewer transistors than current GPUs, which must support complex floating point math. This would make high-performance AI chips significantly cheaper to produce. This enables a practical privacy model. Devices with limited power and memory can run reasoning models locally, processing sensitive data without pinging a cloud server. By simplifying the underlying mathematics of the transformer layer, bitnet addresses the memory bottleneck at its source. This shift moves high-parameter intelligence from dedicated server racks to the standard CPUs already present in everyday hardware.